going to start with ratios, proportions, units, percents. This is two-part, using ratios and proportions to solve problems. All right. The most fundamental thing to understand is that a ratio, it compares two things. It compares two quantities. Most of the time, mathematically, we're using ratios as fractions. Okay? So we're going to be using fractions and proportional relationships to analyze and solve different problems. All right? So here we have a show. 240 adults and children attended the show. Okay? So this is the total of adults and children. The ratio of adults to children was 5-1. This is the first way that you'll see a ratio written out as a phrase. A number compared to another number. So what that means is that for every 5 adults that went, there was also 1 child there. Okay? So we have a ratio of 5-1. Another way that we can write this is using a colon instead of the word 2. It means the same thing, 5-1. And then using as a fraction, we can write a fraction of 5/1. When you're using fractions, label what the numbers are. That way you don't forget and you understand the things that you're comparing and you're less likely to make a mistake because we'll be using the fractions. We'll be using the fractions to actually perform our calculations. Okay? So we have 5 adults for every 1 kid. Okay? So if I have 10 adults, how many kids is that? 15 adults, how many kids is that? 3. Those are all equivalent fractions. 5-1, 10-2, 15-3. These are all equivalent fractions within our ratios. Now, this one's a little bit different because the number that they give us is a total. Okay? So we kind of need to readjust the way that our ratio is and think about a total. All right? So if I have 5 adults for every 1 kid, what's that total? 6. So we can think of it as out of every 6, or for every 6 person, or out of 6 people, I'm thinking how to do that, plural. Every 6 people, I'll have 5 adults. Or out of every 6 people, I'll have 1 kid. So we can still use the information in that ratio and adjust it that fits our scenario and the other information that we have. So they told me 5-1 for kids and adults, or adults to kids. But then that's a total of 6 people. So 5 adults for every 6 people, 1 kid for every 6 people. And we need to do this because what they give us is a number of people. Total number of people. All right? So using this ratio, we want to figure out how many children attended the show. Well, I've got 2 ratios that uses total, one with adults and one with kids. Which one should I use? The one with kids, because that's what they're asking for. How many children attended the show? So once we have our ratio that we need, we can set up our fraction, 6 people total, and then for every 6 people total, one of them is going to be a kid. And we're going to set up a proportional relationship where we're comparing 2 fractions. We have 240 people total. I want to know how many of those are kids. So we have a proportional relationship. Those 2 fractions have to be equivalent. In the broadest sense of the term, we're asking ourselves, what can I multiply 6 by to get 240? And we'd want to do the same thing to 1 to figure out how many kids. All right? Algebraically, we could set up 6 over 1 equals 240 over x and solve for x. Multiply both sides by our least common denominator. Now with proportions, we have a little bit of a shortcut through that algebraic process called cross multiplication. We multiply both sides by the opposite denominator, which allows us to then solve for our variable. I will do 6 times x and 1 times 240. And then solve for x using division. What do I get? 40. So the number of kids is 40. Okay? So when we're using proportional relationships, we can use that shortcut of cross multiplication, which is the same thing we do if we're trying to clear out fractions. We're just multiplying by the least common denominator. So our fractions get cleared out, and then we can solve for our variable. So we've got that proportion. Okay? Questions, comments, concerns? All right, then roll. All right. So, given a location and a time of day, it might be true that a fence post that is 4 feet tall casts a shadow that is 6 feet long. Okay? We want to write the ratio of the height of the object to the length of the shadow. So we need a ratio that's comparing height to length. Height of the object to length of the shadow. Well, what is the height of my object?
12 foot. Or not that.
4 feet.
Where is it?
Right here in the question. A fence post that is 4 feet tall. So the height is 4 feet. Okay? What's the length of the shadow? 6 feet. So we've got our ratio. Now remember, ratios can be written as fractions. Can I simplify that? So I end up having an equivalent ratio of 2 feet to 3 feet. So we can always simplify our ratios as well. So you need to keep that in mind. Maybe this is multiple choice. They're asking for the ratio. And you don't see 6 to 4 or 4 to 6. 2 to 3. Recognize their equivalency and you'll know that they're the same. They're going to give us the same representation. Every 4 feet to 6 feet is going to be the same as every 2 feet to 3 feet. So now using this ratio of height to length, using this fraction of 2 feet in height represents 3 feet in length, we can now evaluate a couple different scenarios. At the same time of day, how long of a shadow would a 6 foot tall man cast? Am I going to put that 6 in the numerator or denominator of my other fraction? The numerator, because it represents height. And then I'm solving for the length of the shadow. So we use our cross multiplication again. Go ahead, tell me, how long is our shadow going to be? 9 feet. 3 times 6, and then divide by 2. Same ratio. 2 to 3. How tall would an object with a 12 foot long shadow be? Is that going to be my numerator or denominator? Denominator, because it's talking about the shadow. The denominator is shadow. We solve for our numerator. How tall is that object? 8. So what we can do is we can write an equation that models this relationship. And what this comes down to is, what we're about to do is actually fundamentally the first type of linear equation that you would have ever learned about. Okay? It is a proportional relationship where it's always going to be that constant ratio. So let's look at our ratio of 2 to 3 and think back that, remember, it represents height and length. All right? 2 to 3 represents the comparison of height to length. Well, what we're going to do is actually just use variables to represent height and length. And in order to write our equation, we just need to solve for one of the variables. Get one of the variables by itself. And we're going to do it with both of them so you can see the different process. But if I wanted to write an equation that models this relationship of height to length, height to length, then I'm going to solve for height. I'm going to get h by itself. Well, how do I get that L out of the denominator and away from the h to the other side? Multiply by L. Since that's h divided by L, if we want to multiply by L, it's going to cancel out here, and h will equal 2/3 times L. So there's my model for height to length. So I can take any length that I have a shadow that's 3,000 feet long. Plug in that equation, multiply it by 2/3, boom. I've got the height of the object. That gives me a shadow that's 3,000 feet long. If I wanted to flip it the other way, well, we need to solve for L. So if I have h equals 2/3 times L, how do I get L by itself? Divide by what? I want L by itself, so I want to get rid of that 2/3. Why? How do we get L by itself? By what?
2/3.
That'll give me 4/9.
You multiply by 3.
3/2. You want to multiply by your reciprocal. So we multiply by 3/2. So those will cancel. L is 3/2 times h. So same relationship, different perspective. Now if I say, okay, I have a building that's 5,000 feet tall. How long would its shadow be? Plug it in and solve. This is our very, very most basic linear equation. It's one where our y-intercept is 0. When we have a proportional relationship, our y-intercept will be 0. All we have is a slope. We call that slope the constant of proportionality. Okay, that was our first introduction to slope when you were in middle school, whether you remember it or not. Constant of proportionality is that ratio of the relationship. So, using that ratio, we could go through and we could solve. 7 pounds of plums make 8 rolls of fruit leather. Do you guys really still have fruit roll-ups? Oh, man, those are so good. Every batch of fruit leather, fruit roll-ups, requires the same amount of plums. How many pounds of plums are required to make 20 rolls of fruit leather? So what would my ratio be? What's the ratio for that scenario? 7 to 8. 7 what? Pounds. So let's label it so that we remember what these are. For my international students, IBS is your abbreviation. What's LBS? Why? I don't know. Ask the English. And 8 what? 8 rolls. Okay? If every batch of fruit leather requires the same amount of plums, how many pounds of plums are required to make 20 rolls of fruit leather? So what am I going to set this equal to? Guys, how many pounds, that's what we're solving for, over 20 rolls of fruit leather. So go ahead, do your cross multiplication. What do you get for x? Should be one of those 4 numbers. So we get 17.5. Now, fun fact, you can get that answer without having to write down a single number. Because with the answer options that are given, we can use some inspection to eliminate ones that don't make sense and then narrow down what's going to make the most sense. So, looking at just this, 7 pounds of plums makes 8 rolls of fruit leather. And I want to know how many pounds to make 20 rolls of fruit leather. Which of these two answer options can I eliminate right off the bat?
A and B.
Why?
Because it's below the amount of pounds.
Yeah, and we're making more than 8 rolls, so we would have to have more pounds of plums, right? Also, 7 and 8, those numbers are pretty close together, right? So it would make sense that however many plums I need would be close to the number of rolls. These two numbers are way too far. So we can eliminate those two right off the bat. Now, if I'm making 8 rolls, okay, and then I'm going to make 20 rolls, do I have more pounds of plums or fewer pounds of plums to make the rolls? Fewer. So we need to pick the one that has fewer, not more. 7 pounds is less than 8 rolls. 17.5 pounds is less than 20 rolls. Okay, so you can still use some of that inspection and that intuition to roll through your answers. Save you a little bit of time rather than trying to do 7 times 20 divided by 8, see what the answer is, make sure it matches up. You've got multiple choice, use that to save you some time. Now this one is fun. I like this one. This is the last one, right? Yes. All right. Stick with me because there's a lot going on here. All right. Erica plans to purchase seed to plant grass in a large field. She has a map of the region and calculates the area of the region on paper to be 180 centimeters squared. So let's pause there. It's a map, it's a map, it's a map. Got a map. The area of that map is 180 centimeters squared, which means she measured the length and the width with a ruler, multiplied them together, we got the area. Does that make sense? Follow me so far? Okay, so we have the area on the map. All right, the scale on the map shows that 1 centimeter equals 20 feet. Okay, so there's a ratio, 1 to 20. Now she plans to cover every 400 feet squared with 1 pound of seed. How many pounds of seed will she need to cover the entire field? Well, the first thought is that we have to know how big the field is. Okay, so let's draw another little picture. We've got a map, and now we have the real field. Okay, in real life, IRL, in real life. Okay, we don't know what the area of the field is. Okay, what we do know is based on our scale. She says, okay, if I measure 1 centimeter on the map, that corresponds to 20 feet in real life. Okay? And so, however many centimeters long equals so many number, 20 times the amount in feet on the length. Same thing on the width. I can say, okay, well, from here to here is 1 centimeter. So from here to here is 20 feet. All right? With me. What is the area of this little square on the map? Say again. Someone said something. How do I find the area of that square? Times width. What's the length?
1.
What's the width?
1.
What's 1 times 1?
1.
So what's the area of that square? 1 centimeter squared. Okay? So 1 centimeter equals 20 feet. This area is 1 centimeter squared. Now here, I don't have 1s anymore, I have 20s. What's the area of that same plot in real life? What's the length times the width, y'all? 400. Is that the same ratio that I had here? No. Now it's 1 centimeter squared to 400 feet squared. When you go from linear to area, well, area is squared. So it's 1 squared is 1, 20 squared is 400. Your ratio changes. Now, that right there is the concept that this question is trying to test. Because there's a long way to do this and a fast way to do it. And if you understand that that ratio changes when you go from linear to quadratic, then that's what allows you to do it the fast way. Because the long way is, okay, we'll find the area by finding that it's 20 by 20, and then we'll use that proportion in order to figure out how much space is in the entire area, and then use that to work backwards to figure out how much we need. Okay? But the fact that this is 400 and that they're using this is not a coincidence. They did that on purpose to make it easier. Erica plans to cover every 400 feet square with 1 pound of seed. Okay? So for every single one of these squares, I'm going to use 1 pound of seed. Okay? Well, let's look at the map. For every one of those squares, it's going to be 1 pound of seed. Because they represent the same thing, right? One's just real life, the other's a drawing on a map, but they represent the same spot of land. So for every single one of these 1 centimeter squared chunks on the map, I need 1 pound of seed. How many 1 centimeter chunks or 1 centimeter squared chunks am I going to get out of 180 centimeters squared? $180. It's 1 centimeter squared. In order to get 180 centimeters squared, I need 180 of these. I need 180 1 centimeter square squares. So how many pounds of seed does she need? 180. They chose 400 on purpose because that's the area there. The most common misconception would be saying that, okay, the area here is 1 centimeter squared, so in real life it's going to be 20 feet squared. It's not how that works. Because you're adding dimensions. So 1 centimeter squared on the map is 400 feet squared in real life. Well, every single one of those needs a pound of seed. I've got 180 of those on the map. I've got 180 of those areas in real life. I need 180 pounds of seed. So it's making those connections. The long way would be to set up your proportion. 1 centimeter square to 20 feet, or I'm sorry, 1 centimeter to 20 feet. Okay, 1 centimeter to 20 feet. And then, actually no, we'd have to do the conversion first. Yeah, 1 centimeter squared to 400 feet squared. And say, okay, well I know my map is 180 centimeters squared. How much is the area of the field? Well, we'd have to cross multiply and solve, and we'd find that the area of the field is 720,000 feet squared. And say, oh, okay, well, I know the total area. Well, I know for every 400 feet squared, we're going to use 1 pound of seed. So that answer will give me how many pounds I need. Well, that answer just takes you right back to the 180. That's the long way. Assuming you didn't mess up your ratio. But they made it easier by making it 400 so you can see the connection. It's going to be the same as the 1 centimeter squared and the 400. It is the ratio. So you just take the 1, okay? Questions, comments, concerns, queries, or... Now, this is the baseline. There may be some variations, but all the skills that we did here are the skills you're going to be using for your ratios, your proportions, your percents. Okay? We're going to be adding to